Hello? Okay. Hi, everyone. Thank you for joining us today for our Summer Astro Colloquium series. My name is Rav Kaur. I'm a rising senior at UC Berkeley, majoring in astrophysics and music. And here I'm working with Roseanne DiStefano on X-ray binaries.
Hi, my name is Ramisa Akhtar-Rahman, and I'm a rising senior at William & Mary, majoring in physics and minoring in English. I work with Joshua Lovell, David Wilner, and Eric Koch this summer on characterizing young stellar objects and radio wavelengths. And we're both summer interns in the Astro REU program.
So it is our honor today to introduce today's speaker, Dr. Kaley Brauer. Dr. Brauer is an alum of our very own Astro REU program. She was here in 2016 and she studied X-ray binaries like me. During her undergrad at Brown University, her research interests ranged from topics in astro and machine learning to renewable energy. After completing her undergrad in 2017, Dr. Brauer went on to MIT for her PhD. At MIT, she studied early small galaxies and how they contribute to the formation of the Milky Way, which is what she'll be talking about today. During this time, she was a Department of Energy Fellow, and she also worked at the Lawrence Berkeley National Lab for a short time. After finishing her PhD program this year, she is back at the CFA as a NSF postdoctoral fellow, and she's working on simulating early galaxy formation with individual stars.
In addition to her research, Dr. Brauer is involved in many scientific outreach activities. She has received NSF funding for illustrating and publishing children's books in astronomy. She also runs a weekend space camp at Harvard for middle schoolers, and worked with public schools in Everett on computer science and cosmology education. In her free time, Dr. Brauer enjoys painting, dancing, hiking, and zooming around on her moped. Please join us in welcoming Dr. Kaley Brauer.
All right, thank you. So I'm extremely excited to be here today to tell you all about my work on the legacy of the first galaxies. And just to set the scene for the talk, I wanted to show this painting of mine of two galaxies merging that is actually based on a real Hubble image. This is the real Hubble image, just to show how beautiful these systems are, and that these are real images that we're able to capture in the universe. Before I get too much into the history of the universe, though, I'm going to first give you a brief history of myself, even though you just heard one, just a little bit more detail about how I ended up here standing in front of you guys today. So when I was in college, I actually started out wanting to be a scientific illustrator, but for a number of reasons, including the fact that art is actually quite difficult and science is really cool. Not to say that art is also very cool. I ended up going more of the science route, and a huge contribution to me making that decision was my experiences in REUs like this one. So I had my first experience with astro research at the SETI Institute, Search for Extraterrestrial Intelligence, and NASA Ames. This was me in 2015 being very excited to rotate a large telescope at Lick Observatory. And then, already mentioned, but I had an absolutely incredible time here in 2016. This is a picture of us from back then with Jonathan as well, with both Jonathan and Matt here as well. And I am still close to basically everyone in this photo and had just an incredible time working here at the CFA. And in fact, I managed to track down a photo of me standing in this exact spot 7 years ago. Very bad photo, but it's evidence. This was me 7 years ago presenting my work from the REU, just like you guys will be doing in 2 weeks or so. So extremely excited to be able to interact with you all. After that, I wanted to try out a few different types of research as well, so I switched to studying batteries and some machine learning things. This is the one and only photo of me ever talking about batteries, because I ended up switching back to astro right after, just because astronomy is incredibly cool, and I can't believe this is a job. So I am extremely excited to still be able to be doing this today. This all culminated with me getting my physics bachelor's from Brown in 2017, and after which I applied to several PhD programs and ended up going to MIT, as just mentioned, up until extremely recently, you see 2023. And I had a wonderful time in my PhD for a number of reasons, mostly the people, because it all, science is about the scientific results, of course, but it's also really about the people. And I had a really great time working with both my cohort and with my collaborators. But something I wanted to specifically mention to you all here today also is that a reason why I enjoyed my PhD so much was also the opportunities I was able to find to do a lot of really cool things. So I really wanted to highlight and encourage you guys to just apply to tons of stuff. And in fact, I want to highlight some of the things that I applied to that I really think were really cool and that you guys should take note of if you're interested in them at all. But I applied to tons of fellowships, programs, conferences, travel grants. They don't all pan out, of course, which is why I tried to apply to anything that looked interesting. But one of the ones that I want to really point out is this program that I was in for 4 years. I was a fellow of the US Department of Energy. They paid for my PhD. And this is a national fellowship similar to the NSF GRFP, if you're familiar with that, but better. And it's my opinion, but it's also not, because it's more funding, more years. It has additional support. They put you in this cohort of wonderful fellows that you get to meet with every year when they fly you out to DC as part of this conference. And this is a picture of me talking in Washington, DC about my work as a computational science graduate fellow. So that's what the CSGF is. So if you're interested in computational work, this is a really wonderful fellowship that you should apply to. These are all PhD specific, but if you guys are interested in PhDs, I would like you to keep it in mind. Also, as part of this, I was a visiting fellow at Lawrence Berkeley Lab. So I spent a semester at Berkeley, which is just nice to go meet more people, try slightly different research. And this was possible due to the Department of Energy funding it. So this is a bonus part of the CSGF program. And an additional thing I really wanted to highlight, because I think that this program is just so cool, is that there is this program, this school, called the International High Performance Computing School. I was lucky enough to be a student of it in 2019, and then later I worked at the school as a mentor in 2022, so last year. And this is for PhD students and even postdocs who are interested in incorporating more computing into their work. So you don't need to be already using high performance computing. And in fact, it's better if you're not, because you can go to this school and really just get this crash course learning about a ton of different computing things over the course of 1 week, where they pay for all of your flights, all of your food, to go to these really incredible locations with, once again, really cool people. So in 2019, I went to Japan, and then this is us in 2022 in Athens, Greece, just learning a ton and seeing a ton of really cool places. So I definitely recommend you look into that. And I have more things. If anyone else is interested in more things that they think are worth applying to, you can definitely contact me. These are just a few. So that all leads to, this is me last month, being officially conferred my degree. So still very excited to be called Dr. Brauer. It's extremely fresh. Yeah, so June 2023, I got my degree, and then I started here as an NSF fellow, postdoc fellow, just a few weeks ago. So yeah, very big move right up the street from MIT. So that was a brief history of me. Now to brief history of the universe. And of course, I'm happy to answer any questions about my own personal background at the question portion. But all right, science time. So a brief history of the universe, just to walk you through really quick the things that are relevant to at least what I'll be talking about. The universe is around 13.7 billion years old, with this Big Bang occurring, way back in the past. And shortly after the Big Bang, after some inflation, some cooling, some expansion, there were still no stars yet. And so this is what's called the Dark Ages. So there was no stars in the universe for a portion of time, and they only started forming a few 100 million years into the universe. So we start getting the first stars a few 100 million years. And then directly after that, we start getting the first galaxies, which are, just systems of stars and gas. And those are just a little bit after, forming within the first billion years. Still early on as well, there's this period of the universe called reionization, which I'm not going to get too much into the details of that if you're not familiar. But it is this period where radiation from the first stars starts ionizing the material in the universe. And this is going to be important later on, so I'm just going to point it out in this history here. And then ever since this was all fairly early on in the universe, there's just been this expansion, more stars, more galaxies, planets, until we reach present day with everything that we can see around us now. So the first galaxies. So I just said, the first galaxies formed within the first billion years after the Big Bang. And every galaxy that we see today, including our own galaxy, the Milky Way, is a result of mergers that started with these very first galaxies. So these first galaxies seeded the formation of everything that we can now see today. And something I want to point out is that the very first galaxies are too faint to be directly observed by even JWST. So the most miraculous technology humanity has created to study the stars and the galaxies, even with that, this is beyond our capability. We can't see the very first galaxies. But we're really interested in them. We want to learn about our own history. We want to learn about how the Milky Way came to be, how it is today. So how are we going to study these things that we can't see? That, of course, is going to be something that I get into a little bit later in the talk, but I just wanted to point out the difficulty of studying some of these things. As some background, for those of you who are not familiar with galaxy formation, the basic way that galaxies grow is through mergers. And so this is just a little visualization. It's not real. There's complex physical processes involved and things like that. But this is the basic idea. You get several galaxies, you keep merging them, you get bigger and bigger galaxies over time. And this is a visualization, but this is a real image. So this is a real Hubble image of the mice galaxies, so-called because I have here it is. You can see these tidal tails here flying off. And this is just an example of an ongoing galaxy merger that we can observe and take pictures of. So what about our galaxy, the Milky Way? In case you are not particularly familiar with the Milky Way, I would love to introduce you. So Milky Way, everyone Milky Way. Thank you for the few giggles there. But this is a top-down view of the Milky Way, showing the spiral arms. So the Milky Way is a spiral galaxy, barred spiral galaxy. So here in the center, you have the bulge and the bar with these spiral arms with high density of star kind of spiraling around it in the plane of the galaxy. And then if you look from the side, you can see we're looking once again into the plane of the galaxy here. I'm just going to break down the components to familiarize you. You have the bulge in the center with a bunch of really old stars. You have the thin disk, which is actually where we are located, about 8 kiloparsecs from the center. This is where the majority of the ongoing star formation is occurring, as well as the thick disk, which is kind of puffed up around, also with this is where a lot of the action is happening, where ongoing stars are found and high density of stars are located, and that's the spiral arms is down in that area. But there's also interesting stuff if you look farther out. So this is what's called the stellar halo here in the outskirts. It's the extended luminous outskirts of the galaxy. And this can go out, so this is not to scale. So this can go out, dozens to, maybe 100 kiloparsecs out. There's no set cutoff, but out in this area, we have a bunch of old interesting things, like we have dwarf galaxies that orbit around us. We have globular clusters, which are these collections of stars. We also just have, rogue metal poor stars we can find that have been stripped off of galaxies during mergers. All this is located on the outskirts. And if you go even farther out, you have the dark matter halo, which is holding it all together. So galaxies form hierarchically, which is just the scientific term for saying that they grow through mergers with other galaxies. We know this to be true. We know that to be the general idea of how the Milky Way came to be. But what about the specifics? How exactly did the Milky Way form? This question is a major question of the subfield of galactic archaeology. So similar to Indiana Jones, who studies the history of human civilizations by finding and interpreting artifacts, galactic archaeologists like myself study the history and the formation of the Milky Way from using our own types of artifacts, which in this case are detailed observations of old stars, gas, dwarf galaxies that are around us, anything that we can see today and use to piece together the story of the past. So this is the goal of galactic archaeology. And so this is the sort of thing so today we can see the galaxy as it currently is. But what we want to know is kind of this map of all the mergers that occurred to bring us to this point. We want to learn about our own history. And this is what's called a merger tree. You can see how it looks kind of like a tree. This is a very simple version. The actual Milky Way merger tree is much more complicated than this example, but similar to this example, the actual Milky Way merger tree, we expect to have only a few what we would call major mergers. So you can see here with these large, like kind of similarly sized galaxies. Those are some of the larger mergers. But there should be a ton of tiny galaxies that merged into us. So only a few of the big ones, but tons, possibly over 100 of these really little galaxies, early small galaxies, merged to form us. So that is something that we expect from simulations, but in reality, we don't actually have we don't understand those little galaxies that well. They're really hard to study. They're little, they're old, they're small. So that has been my goal throughout my PhD, and something I'm working on now as well, is to understand the little stuff in the history of the Milky Way. So the little stuff, in the technical terms, is called ultra-faint dwarf galaxies, or UFDs. This is the smallest classification of galaxy, and it's any galaxy with a luminosity less than 10 to the 5 solar luminosity. And this is just one picture of, this is called Reticulum 2. It's a ultra-faint dwarf galaxy that's orbiting around the Milky Way today. And we've detected, quite a few, at this point, what are we at, like 15 to 20 of the ultra-faint dwarf galaxies for which we have like really good spectrum and things like that. But there's, dozens of them around us today. And what's exciting about the little stuff, both the ones that are currently surrounding us and also the ones that already merged, is that these galaxies are largely relics from the very first galaxies. To pull up this picture again, the ultra-faint dwarf galaxies are largely galaxies that started forming. So they early on they started forming the first stars. They're some of the very first galaxies, and they got just big enough to start forming stars. But they were sufficiently small that when reionization occurred, they actually were quenched by reionization. They're kind of fried, and they were unable to continue forming stars after that point. So these galaxies, ever since reionization, have kind of just been hanging out. They're these little time capsules of stars that have, and gas that existed early on in the universe, and now have not largely changed to present day. And so these are artifacts that I'm interested in, is these ultra-faint dwarf galaxies, and specifically stars from these ultra-faint dwarf galaxies. Both to, learn about these early galaxies forming and learn about the early stars forming. And the way that I study these is through galaxy simulations. This is a video from Illustris. So Lars Hörnquist here, for example, was one of the major Illustris people. This is a large galaxy formation simulation. And if you were to run something like this on your laptop, it would take thousands of years. Luckily, we don't run them on laptops. We run them on supercomputers. But even then, it takes months to run, plus however many months of human development. And so these are incredibly complicated, physics experiments run through computers to test different models, compared observations. and also just make, some of these beautiful videos. So this is, Illustrious is just one of several. I'll talk about several simulations throughout this talk, including ones that I've only analyzed and ones that also I've been developing. But this is a really good way to study galaxy formation, is to let the computers run the different models and then learn about the implications and how they compare to actual observations. So, galaxies are junkyards. And what I mean by that is that the stars from accreted galaxies, which are the galaxies that merged into us, when they get pulled in, their stars are strewn all around the galaxy. So this is true all throughout the galaxy, but is especially true and useful in the outskirts of the galaxy, where there isn't as high a density of the in situ stars, like the Milky Way's own stars. So you can find, this is an artist example, you can see how, some incoming galaxies here have been pulled into streams as they merge, and their stars end up all over the place. And just to visualize this is a little simulation showing a galaxy merging with a Milky Way-mass galaxy. And so the red stars end up all over the place. So if we were interested in finding the red stars, you could see how that might be difficult after a bit of time has passed and they end up physically all over the place. And this is true for every merger that occurs. And so the remains of galaxy mergers are all throughout our galaxy, just all over the place. So how do we find and classify the junk? Because that is the way to build that merger tree that I was talking about, is by finding what's in the galaxy, determining its origins, and starting to piece together that history. So that's something we want to do, is find and classify the junk, and I specifically want to find and classify junk from the smallest galaxies, because that is something that has been historically very difficult and presently very difficult to do. One way to do this is by observing chemical abundances of stars. And I'll explain why chemical abundances are useful in a second, but first just to define chemical abundances with a bit of background for those who are not necessarily familiar. When you get a spectrum from a star, that is the light from the star measured at different wavelengths. So you get the white light, and then if you break it up into different wavelengths, you can see how strong it is at different wavelengths, and get something like this line here, where you have the strength at different wavelengths that would correspond to different colors, such as in the top bit here. So this is showing the same spectrum pictorially in two different ways. This is actually a solar spectrum. Usually the spectra are not as nice as these. But when you get a spectrum, it actually reveals the chemical composition of the star that you're looking at. The reason is because, depending on how familiar you are with nuclear physics, certain chemical elements absorb or emit at certain wavelengths. So if we look at this spectrum here, look at right here, so Fe is iron, and we know from nuclear physics that iron absorbs light right at this wavelength. And so if we look at this spectrum and we see a dip right at this wavelength, we can say that there is iron that was in the star. And if you have a really strong dip, it was a lot of iron. If you don't have very much dip, less iron. So by doing that for a bunch of different points on this spectrum, you can learn about the chemical composition. You could also kind of think of this as the barcode of the star, especially because if you look at the rainbow version of this, where the dips in color here are absorbed points, you can see how it can look a little bit like a barcode. This is useful because stars remember where they were born. So of course stars fuse chemical elements, but that's in their center. So if you're looking at light from the surface of the star, that actually doesn't change. So if you're looking at the chemical composition of the surface of the star today, it's kind of a snapshot of the chemical composition of the gas that they formed from, however many years, billions of years ago. And so if you, for example, see two stars with very similar barcodes, then you can say that they formed in very similar environments, potentially together in the same galaxy. And so this can be a way to start piecing together, and it's called chemical tagging. It's identifying stars with similar chemical compositions to learn about their origins. I also wanted to point out some specific chemical elements that I have been interested in. These are chemical elements formed from the R process. R stands for rapid. This is a way of forming really heavy elements through the rapid neutron capture process, where you have a nucleus and you bombard it very quickly, rapidly, with a bunch of neutrons to get it really big and heavy and unstable. That's the center point here. And then once it's really unstable and heavy, you will beta decay to stability, which means some of the neutrons decay into proton-electron pairs, and then you end up with a new element, and a new heavier element because you've added. This is one of the two main processes that forms all the heavy elements in the universe, including, if any of you are wearing gold, this is usually the one that makes the headlines because this is the way that gold is formed. Also silver, platinum. So our process, you can think of it like our process, or not, that's fine, depending on how mature you're being that day. But it's also cool because actually the only confirmed site of the R process in the universe, because this requires a really high density of neutrons, it's just chaotic environment physically. The only confirmed site is when two neutron stars collide. So this is a video of how this might happen from LIGO. But if you're wearing any, gold, platinum, silver, it formed through something like this chaotic like jet outflows from the accretion disk where we can see, so we're able to observe kilonova with decay, like that basically has confirmed that you're forming these chemical elements through the nucleosynthetic process of the R process. So pretty cool. And just throwing up the periodic table, these are colored based on their astrophysical origins. So, of course, you get some elements just from the Big Bang, others from certain, fusion or supernova, and the R process is everything in purple on this. And so you can see here, that's a lot of elements, and specifically a lot of the heavy elements. So it's a very important process. Okay, so this is relevant to my talk because when I say we, I really mean my wonderful observer collaborators like Alex G., who's at UChicago, have observed ultrafaint dwarfs with strong R process enrichment, which means that we get spectra from their stars and see that they have a lot of these chemical elements, which is rare. It's rare to see stars with a lot of these elements. So it was a big deal when this is reticulum 2 being shown here. It was a big deal when Alex first saw that the stars in this tiny dwarf galaxy were all really strongly enriched. And it started making us think, could there be a link between strong R process enrichment and these tiny dwarf galaxies? The reason why this could be plausible is, well, I guess first of all, we've seen it. We saw it with reticulum 2. Since then, we've seen it with Tucana 3, which is another ultrafaint dwarf. And also, it's plausible because these small dwarf galaxies have really low star formation rates. So if you manage to have an early R process event, then all the subsequently formed stars would have really strong, clean R process signatures on their stars. So this could be a method so it does seem like this is a method of forming these stars, but how significant is it? Like, is this link significant or not? So this is just the hypothesis to sum it up. We have the Milky Way sometime in the past, a bunch of small ultrafaint dwarf galaxies emerging into it. Some rate of them have had an R process event occur and are now very strongly enriched. If this is true, then we could track this to present day, and we could observe today, we can identify these R2 stars, which are just stars with a lot of R process, in the stellar halo today, and we could observe this and learn about the past, both learn about the number and types of ultrafaint dwarfs, about the rate of enrichment, and it could be a way of identifying stars from these tiny galaxies. The way that I study this is with a simulation suite called the Caterpillar simulation suite of 35 Milky Way-mass galaxies. This is useful because all of these Milky Way-mass galaxies have slightly different formation histories, so able to get kind of some statistics versus just having a single Milky Way forming with only a certain single set number of ultrafaint dwarfs. This was much more variation. And so we studied this and got some statistics on what happens if you only form highly R-process enhanced stars in the tiny ultrafaint dwarf galaxies and nowhere else. And what we found was that there actually could be a link. So this is, I'll walk you through this main result plot. But basically, if you look at the Milky Way today and you observe it as it is right now, you can see that about 3%, but of course with uncertainty, so we're going to say 2 to 4% of the metal poor stars are highly R-process enriched. So that's we're going to call the R2 fraction, and that's the range of it that we can observe today. Then, if we only form these types of stars in ultrafaint dwarfs, we can already account for around half, obviously with a range of uncertainty depending on different parameter choices, different accretion or different formation histories, but a significant fraction of all these stars through this single origin. This is surprising because the chances of a random star being from a UFD, being from an ultrafaint dwarf, is less than 1% chance. So if there was no link, instead of this range being here, it would be down near 0. But the fact that it is well above 0 is intriguing and made us start thinking that this could be important and that there could be a significant link, and this could be a way to identify stars from the ultrafaint dwarfs. All right, so this is a lot of talk about chemical abundances, specifically the R process chemical abundances, but we can also measure other things about stars. So what else can we measure? And for example, we can measure stellar kinematics. So these are kinematics from Gaia of, I believe this is 40,000 stars going around the Milky Way. And for anyone interested in stellar kinematics, right now is an extremely exciting time because the Gaia Observatory, which is a space observatory, has just revolutionized the field of stellar kinematics. It's currently obtaining, I think we're at over 2 billion kinematics of stars in the Milky Way. Just an absurd amount of data. And so Gaia is just pumping out tons of information, and people are learning a ton from it. And just to kind of drive home how far we've come, I went and found the oldest map that I could find of the Milky Way. This is from 1785, and this is peak astronomy in the 1700s. This is from William Herschel. I guess I should note that Caroline, William's sister, was also an astronomer who was often not credited, so this may also be her work. So William/Caroline looked at the sky and drew by hand their best guess of a map of the Milky Way. And this was the best map that we could make in the 1700s, was this right here. Versus, as of 2020-ish, this is the current best map of the Milky Way. It's this beautiful data release from Gaia. And you can see just a ton of detail. So there's dust obscuring lots of portions, but you can see Magellanic clouds. You can see, so this is all the plane of the Milky Way. And there's a ton of detail in this image. But as I mentioned, Gaia measures kinematics. So to get an even better feel, this is the proper motions of 70,000-ish stars going across. And this is just a tiny fraction of the data that Gaia has been reporting. So it's a lot more than what we knew in the 1700s. And it's a lot more than we knew 10 years ago. It's a ton of information. So this has been a really exciting time for people who like to look at stellar kinematics to learn about mergers and identify mergers. And there's been a lot of work done on some of the major mergers. So Gaia Enceladus, or Gaia Sausage, if you're familiar with that, Sequoia, there's Kraken. There's been a lot of work done. And one of the things that you can do with this kinematic information is you can look for clumps in the dynamic space. I believe everyone in this room has some physics background to some degree, so you're familiar with the idea that energy and angular momentum are conserved. I have an asterisk on this because that's not completely true in a time-varying potential like the Milky Way. But they are quasi-conserved even as they relax over time. So, when stars come in together on a merger event, they physically end up all over the place. So if you plot them in XYZ space, you can't really identify much. But if you plot them in energy versus LZ space, for example, like this plot here by Anamanatsa, you can start to see some clumps that may correspond to stars that accreted together. Because even though they've been moved all over the place, their energy and angular momentum and other conserved actions are roughly conserved. And so this is something that works really well so these are stellar streams that are plotted here. And you can see very clearly that there are clumps. And this is different ways that people identify merger events is through things like this. So I was interested in trying to quantify how well this works for the really small galaxies, because it works for the bigger stuff. Does it also work for the smaller stuff? Just to jump straight to the result, it unfortunately does not work super well for the ultra-faint dwarf stars. There are several reasons for this, but I'm just going to throw up, first of all, the results of one simulation. So let me say first, so I went back to the simulation suite of 35 different Milky Way-mass galaxies forming, and tracked particles from all of the ultra-faint dwarf galaxies and also all the other accreted galaxies. And then traced them to redshift 0, or today, and then looked at their dynamics to see how identifiable they are in different situations. And so this is just plotting the results of where these stars end up in kinematic space, where these are only star particles from ultra-faint dwarf galaxies. So each color, each frame is a different ultra-faint dwarf galaxy that accreted into the Milky Way. And you can already see it's a mess. It's, even just human eye looking at this, it's really hard to identify structure. They're not super clumped, especially the early accreted things. So this is ordered based on when they merged. So the stuff that merged a really long time ago has relaxed a lot, so it's low energy, it's all overlapping, it's not cohesive at all. Later on, you start to see some identifiable clumps up here, but it's only a small fraction. Which is not a shocking result, but it's still a bit disappointing as people wanted to be able to use this method. So generally speaking, ultra-faint dwarf accreted clumps are not identifiable. But rather than just looking at this, we wanted to quantify how not identifiable they are. So with Hilary Undales, who was an MIT undergrad who just graduated, she's going to be going to UChicago soon, we ran 10,000 clustering algorithm tests with 40 dynamics. So I've been showing a 2D slice. We also included 2 additional quasi-conserved dynamics. And we tried different clustering algorithms, radial cuts, hyperparameter choices. We applied fake chemical tagging to some of the data sets to get as idealized as possible. And even in super idealized situations, it just didn't work super well. We identified only a few percentage of the accreted ultra-faint dwarfs at best, and those were the ones that were recently accreted. The reason for this is kind of shown in this plot here. This is the signal-to-noise ratio of the stars from a given ultra-faint dwarf relative to all the other stars in the phase space in that area. Ultra-faint dwarfs don't have a lot of stars, and so they just they relax a little bit more quickly. And so because of all of that, they just get completely drowned out. So you can see the vast majority of them have extremely low signal-to-noise ratio. Just their signatures are way too weak. This was roughly our threshold for identifying them, and you can see there are some that are fully identifiable, but those are essentially only ones that super recently accreted and haven't had time to relax at all in the phase space. So generally doesn't work except for very recently accreted things. Now, this, I guess, result is a little disappointing, not super surprising, but what it really does is reinforce to us the importance of the chemical abundances, because those don't relax. Those stars continue to have their chemical abundances. And there's just a lot more information in there as well. So this has been something that myself and my collaborators have been really interested in, is additional ways that we can use chemical abundance information to identify stars and continue classifying all the junk. And so I have been working on this new frontier of galaxy simulation. That's actually what I'm here to do at CFA, is continue developing and start analyzing these simulations. But I've been working on high-resolution galaxy simulations with really detailed chemical abundances in individual stars. So the interesting part of this is the focus on the chemicals in the individual stars. So this was motivated by our results, but also motivated by the fact that the Astra community is currently obtaining an astronomical, pun intended, amounts of chemical abundance data. So you guys may recognize some of these surveys here, especially H3, which is Charlie Conroy out of the CFA here. And additionally, just a bunch of other surveys here have or will be collecting high-resolution spectra for thousands of stars with much more to come. So we're getting a ton of data. We're starting to get a lot of detail. We're able to observe things like scatter at a given metallicity. You can see scatter in different chemicals that we're not exactly sure the origins of that. We're able to get kind of more information on the distributions in general. And so there's a lot happening on the data side. We want to make sure we're prepared on the theory side as well to compare to all this data that we are and will be getting. So this was the motivation for what we're calling the Aeos simulations. This is cosmological galaxy formation simulations focused on really early galaxies, early small galaxies, with a really detailed treatment of stellar yields. And we have stellar feedback and metal enrichment from individual stars. So that's what these little white dots are here, is a bunch of hundreds of thousands of individual star particles popping up. I'm not going to get into the technical details unless someone wants to ask me directly. But the one thing I did want to point out on the technical side is that we are tracing a number of different metals plus additional metal tracer fields. So we actually have 20 total metal tracer fields, so that we really are able to get a lot of information on the chemicals. And just because who doesn't love some simulation videos? I was just highlighting some of the things we're able to see already, even though we're still running these and developing these. So, right from the beginning, we can start seeing the supernova from the very first stars. This is a temperature projection. So you're able to see energy from these very first supernova flying out into the universe. Also because the potential wells of these really small galaxies early on are very low. So they just fly, all the supernova, just metals and energy and all that just flies out. And then also you can zoom in a ton. So this video is actually from that tiny portion in the corner of this other video. And you can see just the individual stars on this one. So this is actually our largest galaxy, which is why I zoomed in on it here. But you can see the individual stars as a merger occurs. And you can even see little spiral arms starting to form. And it's just an incredible amount of detail that we are starting to see in this, as we get these, tons of particles with tons of metal information. And this is an example of just some of the detail that we're able to get in chemical abundance space. So we have iron here, strontium here, growing up over time. So this is being plotted based on when the stars formed. So you can see that there's these vertical structures here, where at roughly the same metallicity, there is a lot of strontium being formed for different reasons. And so but you can see that these structures, if you trace them back, you can see that they came from different progenitor galaxies, even though this is a single galaxy. This one's from redshift 14. So everything that's in a single galaxy, redshift 14. But it's kind of a proof of concept that it is possible to see different structures in chemical abundance space. These are absurdly low metallicity, but we're just starting to look at the level of detail that we can get in these chemicals, and how we're able to piece that back to the history of the individual galaxies. So there's definitely much more work to come because this is ongoing, and especially we need to figure out ways to deal with the computational difficulty of simulating both galaxies and individual stars and individual feedback and all the things that we're trying to include. But we're definitely currently doing a lot of work understanding abundances and how the stars formed in the first galaxies. So I would just like to put up some takeaways before I get some questions from you all. But one of the main takeaways is that we believe that chemical abundances of stars, including our process abundances, but not only, are a vital way, and due to the concerns about the kinematics, possibly the only reliable way to study the small galaxies and their remnants in the Milky Way today, if we want to find any of the leftovers of those stars in our galaxy. And currently, to help address this and help interpret all the data that we will be getting, my group has been simulating detailed chemical abundances to identify and quantify the contributions from the really faint dwarf galaxies to the Milky Way. So, we want to be able to, measure, I guess this is our process here, but, chemical abundances in general, and start creating the low mass end of this merger tree, such as this one here. So, thank you. I would love to take any questions.
Thank you again for your wonderful talk. Of course, we have some time to take some questions. I have a question. So I know you mentioned how difficult it is, like computationally, to run these simulations. Could you talk a little bit more about how your team's going to go about like optimizing your simulations, or what that process is like?
Yeah, so this is definitely ongoing because we're trying, already the simulation has been stalling quite a bit. And so I guess this is really like a programming question, which is more important than I realized initially would be to physics. But like so far we've been doing different optimizations, like, optimized data sharing, making sure we don't have any extraneous looping and things like that. All that's been kind of Band-Aid fixes. So at the moment I'm hoping to overhaul the code with like a new, so there's like adaptive mesh refinement is a way of, like having just, smaller grid cells around your interesting stuff. You can do that in time as well, which is actually not fully implemented in the current code. And so, for example, every time right now that a supernova occurs and it slows the time step, we want to find a better way of dealing with that. Just getting creative. And also, we're probably going to have to drop certain physics from it as well. So that's the really big question, always like, for whatever question we want to answer, what's the physics that you need to include? Because you can't include it all. So I guess trying to be as clever about that as possible, and we're still figuring it out.
Thank you. I saw you.
How do you select like the scales of what you're looking at? Like simulation-wise, I imagine it would be easier the less area you run it over, etc. How are you selecting like the minimum galactic scales that you need to look at for it to be valuable?
Yeah, so I was interested in not just having a single ultrafaint dwarf. I wanted to have 10 to 15 ultrafaint dwarf galaxies with, distributions that we could measure. And so generally what people do and what I did is you run a parent simulation where like this box, for example, you would run but with only dark matter. And so you can run that with much less computational power you could go to redshift 0 current day if you want, and then you can measure and say, in this box size with these initial conditions, you end up with, 5 ultrafaint dwarfs, and you'd be like, okay, so I want more. So then you would change your initial conditions, do a larger box, check again, and then you can iterate. And then once you like how the end result looks roughly with just the dark matter, then you would start running the full physics models with baryonic physics.
Is there like an initial threshold mass for ultra-faint dwarfs, so they can detect the stream dynamically? Because I assume the ultra-faint dwarf has to be lower than a certain mass, but it has a high mass, right?
So you're saying for for these ones that are identifiable, you're saying are they more massive?
Yeah.
The mass, it's really, so the mass was not a significant portion because these are all very similar mass. Because they're all it's basically everything that's just like just sufficiently massive to have formed stars at some point. So they're all pretty similar in mass. There's still like, maybe an order of magnitude or so difference. But that was not actually the most significant part of them being identifiable. It was just when they merged. And if they merged with a lot of energy, so if they came in with high energy and they merged recently, that was what made them identifiable. Yeah, so it was primarily, I took the other plot out that showed this based on like colored by when they accreted. But you can see a very clear gradient from recently accreted and recognizable to completely mixed. Yeah, so the size was not as big of a deal.
Yeah, so I was wondering if you kind of like made some kind of connection to black hole mergers during like your simulations of like merging galaxies, and like do your galaxies by definition sort of like contain a black hole or no, or like do they not?
Yeah, we actually don't study that, even though that is, so we don't have AGN or anything that is like super affecting in these really small galaxies. They would still largely, many of them would have a black hole, but we don't actually look at that just because with the little stuff, we don't have like the same level of impact as like, the active nucleus of the Milky Way and other things like that.
Do your models include top 3 stars? And
Yes.
how far back do you claim to be able to trace them?
Yeah, so the POP3 stars are problematic for many reasons. We did, so we form these simulations start around redshift, like 130. So we actually had a bunch of different POP3 IMF like choices with different parameter choices, and ended up doing this whole, over the course of like a year, maybe a year and a half, this, I guess, kind of unexpected experiment in unphysical universes, because we found a bunch of ways that the IMF did not work, and we just reionized the universe too quickly, things like that. Yeah, so I still am really skeptical about the POP3 IMF, obviously, because no one knows. But we have to start somewhere, so we pick the model that reionized the universe at a reasonable time, and are gonna try that.
And another quick question.
Yeah.
You showed, excuse me, simulations of supernovae,
Yes.
but you didn't show, and has anybody in the group been considering the effects of gamma ray bursts from the most massive POP3 stars? They're not going to produce supernovae, they'll likely produce GRBs, which some of us here are very interested in and are designing a NASA mission to be able to actually detect these. But are they in your models?
No, we don't. Yeah, so they're not in this model.
They're going to make a big difference.
Yeah, so I didn't show this project, but we did a complementary project studying gamma ray bursts and collapsar models and things like that. We haven't actually included it in this simulation yet. But yeah, I am interested to see how that affects it as well.
Yeah.
Great, this is such a fun talk. So you mentioned one source of our process in Philadelphia. You can imagine that comes after we have 2 stars with supernovas and they collide, kind of like our process enrichment. But you're kind of hinting at this. You could also think that the observers are wrong and there's some really exotic core collapse supernova collapsar that produces our process. Are there any kinematic or chemical implications in your work that depend on that origin of our process or the dominant origin?
Yeah, so I am extremely interested in that. I didn't include it in this just for time constraints. But we haven't looked at the kinematics as yet. But I have one paper out about like studying, I guess, the scatter of europium relative, like how the scatter in europium changes over time with metallicity, or changes with metallicity, if that could be explained by certain collapsar models. Once again, it's really tough because we haven't even confirmed that is a site. It just seems likely and how significant it would be. But yeah, I'm definitely interested. So that's why I was like throughout the talk saying our process event, because a lot of our models are agnostic to how it happens, just when it happens. So yeah, I'm very interested to see how that develops.
Can you give an idea about how many of these R process events there are per dwarf galaxy? I mean, is there unlikely that there would be, there's only 1 in 100, or there's 1 ± 1, or sort of 10 per dwarf galaxy?
Yeah, so our best guess is really just by looking at the surviving ultrafaint dwarfs we can see today, for which we have high resolution spectra. So it's small number statistics, so it's tough, but of the ones we've observed, 2 out of like 17 have strong enrichment. So that's our best guess of the rate based on just what we can see right now. And so that was what these results, wow, I'm going pretty far back, are based on as well. But you can obviously form R2 stars through like inhomogeneous mixing in larger galaxies and things like that as well. So
sort of 20% have sort of one of these events.
yeah, order of magnitude, I would feel safe saying that, yeah.
Yeah, so when you talk about the R process, does that have a like direct correlation to the age range that you're looking at, or does it only like purely tell you about the elements and like how heavy they are?
Yeah, so if we're interested in the age of the star, the R process abundance isn't super useful for that. Usually we would look at, so do I have I don't think I have many chemical abundance plots on here, but metallicity metallicity increases with time roughly, so it's often used as a proxy for time, because early in the universe you don't have any iron yet, and then as soon as stars start forming, you form iron, and you just keep forming iron, and so, well, I'll go to this one. You can see in this plot, as time goes on, it moves across. Like more of the stars, it's not a perfect comparison, but generally speaking, later stars have higher iron. So that's what people often will look at as one of the ways to try to like see relative ages of stars.
Okay, if no one has any further questions, let's thank our speaker today, Dr. Kaley Brauer. Also, if you have any more questions, there's still a few minutes left.
Thank you.
Thank you so much.